Okay, good evening. Today we're going to talk about aerodynamics, some aerodynamic principles. Uh, I'd like to welcome you to the fourth installment of the Private Pilot Ground School. And I'm Kieno Thomas, your instructor. And let's just jump right in. Aerodynamic principles. The science of aerodynamics deals with the motion of air and forces acting on the bodies moving relative to the air moving through that air. Here's a couple cool little examples. We can see the airflow, and we can see disturbances being caused. Here we see a sphere moving through like a baseball or something like that, and we can see it's disturbing the airflow, or the airflow about it is being disturbed. And then we see a sphere with a fairing, which is just a little taper on the back, and we could see less air disturbance. And then finally a sphere inside a housing, and we can see even less of a disturbance. So this is just a diagram to show streamlining. Here we see a vortex being formed as the wing flies through the air. We can see a little small hurricane, or if you want to call it that, or vortex being formed. So here in both cases we can see air moving as a result of a body moving through that air, and we can see air disturbance. Since we're dealing with forces, we're going to have to choose a way to display or label these forces. We're going to use this vectors basically to demonstrate or display these forces. A vector is basically an arrow, and an arrow or a vector has magnitude and direction. Magnitude is more like strength. Direction is where it's pointing. So when we think about our forces, think of force A, or the first force being applied, and then force B, which is the second force being applied, and then C is the resultant. Here again, A, force 1, B, force 2. Here's the resultant vector. Again, A, B, the resultant. Okay, and anytime we see two arrows or vectors having equal magnitude or length, and they're going in opposite directions, so these actually cancel out. So the magnitude is 0, or the resultant force is 0. Here we have the four basic forces that are exerted on an airplane. We have lift, which is the upward force created by the effect of airflow as it passes over the top and the bottom of the wing. We have a downward vector or force, which opposes lift. Come on. So weight opposes lift, so we have lift vector, we have a weight vector. Weight opposes lift and causes the downward pull caused by gravity. Thrust is forward force, which propels the aircraft through the air. It varies with the amount of engine power being used. And drag is a rearward or retarding force, or backward force. Now, drag is not so simple. There's actually a couple subcomponents of drag, and we're going to get into that a little bit later. But for right now, let's just concentrate on the four forces. But understand, like the diagram says, drag or total drag is actually created by a combination or an adding parasite drag and induced drag. So drag is not alone. There's some other things there, members of his family, to help make Mr. Drag up, if we want to call him that. Before we go forward, we need to give two people credit. On the left is Sir Isaac Newton, and on the right, Sir Isaac Newton gave us the 3 laws of motion, and then we have Daniel Bernoulli, who gave us Bernoulli's principle. Sir Isaac Newton, his 3 laws of motion, he created. You can Google it up and look it up as far as when he created it, but basically I want to focus on the 3 laws of motion. The first law is a body at rest tends to remain at rest, and a body in motion tends to remain moving at the same speed in the same direction. Okay, because if you look at in blue, every object persists in a state of rest or uniform motion in a straight line unless it's compelled to change that state by forces oppressed upon it. I just thought that was a little bit rough if you don't study physics or so for our purposes, a body at rest tends to remain at rest, and a body in motion tends to remain moving at the same speed and in the same direction. Alright. An example, you look at this plane, it's parked. It's really not going to move until we fire up the engine and get it moving. Just like this truck. The truck is going to stay parked unless we take the brake off, parking brake off, apply acceleration via gas pedal, and move it. So if it's parked, it's at rest, it's going to tend to remain in rest, and if we start driving, it'll remain in motion. Okay. Unless we come off of the pedal, and it'll even still roll a little bit, and then it'll eventually come to a stop. But that is the first law. The second one is a little bit weird. Force is equal to change in momentum per change in time. For constant mass, force equals mass times acceleration. And that's just expressed in a formula in red on the main. F equals ma. Force equals mass times acceleration. That is basically what this law is saying. And then finally, the third law. For every action, there is an equal opposite reaction. It's just simple. This just deals with when two things act upon each other. Air and a propeller. In previous lessons, we talked about how an airplane pulls it through the air, how a jet engine sucks in air, blows it out the back, and I put air in the propeller there twice on the slide. Disregard that. So the third law, for every action, there's an equal opposite reaction. Okay, we can see the action. The plane is flying. It's a crop duster. It's flying through the air, and it just happens to be some smoke to kind of show what's going on as far as forces. We'll go deep into that in a little bit. Next guy we're going to talk about is a Swiss mathematician named Daniel Bernoulli. He gave us something called Bernoulli's principle. He expanded on Newton's ideas, Sir Isaac Newton's ideas, and further explored motion of fluids in this publication called Hydrodynamica. And I actually put a copy on the slide there. One way we can see Bernoulli's principle is using a device called a Venturi Tube. Now what I want you to pay attention to is, this is airflow or water flow. Alright, and just to show you what's going on, note here we have pressure and velocity. So we have 100 miles an hour of airflow, 15 pounds per square inch. Just watch the numbers as pressure, because Bernoulli's principle states as velocity of fluid, air and fluid act the same way, is increased, its internal pressure decreases. So here, the air or water actually has to move faster. So we went from 100 miles an hour to, at this point, 150 miles an hour. And then we get back to the open end, and we're back at 100 miles an hour. Now something happened with the pressure here. We were 15 psi. We got here, sped up. The pressure actually dropped to 8, just for our purposes. There's no measuring equipment. This is just to give you an idea of Bernoulli's principle and what it happens. So we go from 15, speed up, drop to 8 psi, and then when we get back out, we go back to 15 psi. I always like to think of this as, this is the lunchroom, this is the hallway, and the students are like rushing to get into the lunchroom. That's my corny little example. Now, this is an airfoil. An airfoil is a device used to produce lift. So we could actually see how airflow needs to move over the top of this thing, and we get a pressure decrease on the top of the wing. So now you can see how the Venturi tube is actually applicable to what's going on here. So decreased pressure on top, faster air movement. The air actually has moved faster over the top of the wing than it does the bottom. Velocity increase, negative pressure. For every action, there's an equal opposite reaction. So we get positive pressure on the bottom, and lift occurs. Bang! I just put that little arrow there. So the airfoil provides aerodynamic force when it interacts with a moving stream of air, taking advantage of Newton's third law. For every action, there's an equal opposite reaction, and Bernoulli's principle. As the velocity of a fluid increases, its internal pressure decreases. So it's taking advantage of both of those. Airfoil terminology. Upwash. Upwash, as this plane flies through the air, air actually has to come up to rise up to meet the wing. That is called the upwash, the deflection of the oncoming airstream over the wing. So it actually rushes up to meet the wing and then flows over the top. Downwash. Downwash is the downward deflection of the airstream over the wing and past the trailing edge. So, boom, that's upwash, bang, downwash. So we can see the upwash and downwash here, and I put the little marker there. Leading edge. Leading edge is part of the airfoil that meets the airflow first. As the relative wind approaches, it's going to touch this part first. That is called the leading edge. The trailing edge is the part where the upper and surface rejoin. So we got to think about this airfoil as split. And we have upper camber or curve, and then we have a lower camber or curve. And these two things, they separate here, upper camber, lower camber, and they meet up back here at the trailing edge. Upper camber, I explained what that was. Lower camber, we talked about that. The chord line. The chord line is the imaginary line drawn through the airfoil from leading edge to trailing edge. The relative wind is the airflow that is parallel and opposite to the flight path of the airplane. So our relative wind. And angle of attack. When we look at our chord line of the airfoil and the relative wind, it actually forms an angle here. And that will be our angle of attack. Here we have a couple airfoils, and let's come back to our angle of attack. So the relative wind is actually attacking and forming an angle here with the chord line. Here we have a 0-degree angle of attack. Here we have a 4-degree angle of attack. And then here we have a 10-degree angle of attack. Now, as air circulates around the wing surface, flowing over the top and the bottom, there are going to be regions where pressure is less than and higher than atmospheric pressure. The light blue shows the lower atmospheric pressure, and the dark blue show pressures higher than atmospheric pressure. So you can see light blue here, dark blue is higher. Here, sorry about that. Get the right slide. Here, 4-degree angle of attack. You can see negative pressure on the top because the velocity has increased. Back to Bernoulli's principle. The air has to flow over the top faster than it does the bottom. So we actually have less pressure here. And then we have the 10-degree angle of attack. Now notice that the pressures, they just get lesser and lesser, or the negative pressure increases or decreases, I should say. So I actually think of this as more lift being created. Let's come back to the slide. We have lift being created here, but not a whole lot. But you know, we got a little something going on. Here we have a little bit more. Here we got a lot of lift going on. Okay, and that's because of the negative pressure caused on top of the wing. So it's something we want to be mindful of. The increased lift being generated as the angle of attack is increased, it causes greater generation of lift, and that's just what I said. All right. Now, we use a term called coefficient of lift. It's a way to measure lift as it reacts to the angle of attack. So here we're 0 degrees angle of attack, and we're 5 degrees and 10, and we keep pulling our nose up to 20. All right, here's a coefficient of lift. All right, don't be all mesmerized by these charts. This is just showing you information or data as to what happens. So as our angle of attack is increased, our coefficient of lift, it just gets stronger and stronger and stronger, which indicates us more lift is being generated. All right, they use wind tunnel tests to determine the coefficient of lift for certain angle airfoils. Now, if you note something very weird that happens, you think, oh, we keep increasing the angle of attack, man, we're going to keep getting lift. No, at some point, say about 18 degrees here on this chart, 18 degrees of angle of attack, the lift just drops off, and that will be called a wing stall. The wing just abruptly decreases, the lift decreases, and the wing stalls. Little swig of water there, sorry. Alright, so as the angle of attack is increased, the coefficient of lift is increased. Now, as we're pitching upward or increasing our angle of attack, we have some stuff going on here. At 0 degrees angle of attack, airflow separation is here. A little turbulent wake, nothing to worry about. 5 degrees, we got, a little bit of airflow separation. Now, this is the point where we have what we call laminar airflow. Laminar. Listen to that word, laminar. Think about your driver's license. It's laminated in plastic. It's like the air is attached to the wing. So what happens is the air starts detaching itself, and that's what we call airflow separation. But the separation, it just starts creeping forward at 5 degrees, keeping forward at 16 degrees. All right. This is basically the stall angle. Now, if we keep pulling the nose up to 20, we're not going to get any lift, and the airflow is actually separated from the wing. So there's no laminar airflow sticking to the wing, creating lift anymore. Now, what happens is the nose is going to come down, and you're probably going to come through back to 0 degrees of angle of attack if you do a stall recovery properly, but not to worry. All it is just pushing the nose forward in most aircraft. So that's a stall. It has nothing to do with the engine stall. Oh, the plane stalled. No, it's a wing stall. The wing stopped producing lift. Wasn't very happy wing. The next thing we're going to talk about is aspect ratio. Aspect ratio is the relationship between the length and the width of a wing. And aeronautical engineers, they kind of use this information when they're designing airplanes. And a higher aspect ratio will produce less drag for the same amount of lift. So a lot of times when you're thinking like, okay, well, we need to redesign this wing to do something, to create a certain amount of lift, to do a certain job. Gliders and, say, training airplanes and stuff, the wings look completely different. Moving along here. Aspect ratio of training aircraft, normally around 7 to 9 of an aspect ratio. Here we have a average chord of 5 feet, a 36-foot wingspan. We divide wingspan by average chord, and we come up with 7.2, so that falls in line with our slide. A training aircraft may have an aspect ratio about 7 to 9. And we look at, where's my glider? Okay, sorry about that, guys. Aspect ratio of gliders. Now this one has a high aspect ratio. This aspect ratio is like 25 because of the wingspan. So this wing is really giving you a lot of bang for your buck. But it's a glider. It's not very heavy. Doesn't have a high payload. You can't carry a whole bunch of people. So that's a trade-off sometimes. So that's aspect ratio. Planform. A wing's planform refers to the shape of the airplane's wing when it's viewed from above or below. So we're looking at this airplane from the top. You can see the wingspan, the chord, and the wing area. This is basically a straight, almost rectangular wing. It is a rectangular wing, but it's tapered on the end. No worries. But it will fly like this rectangular wing for the most part. Another thing I want to just you to bear in mind. If you look here, here are the ailerons and here are the flaps. And I want you to just make sure that the ailerons help roll the aircraft. But I want you to note the position there towards the wingtips. There's your left aileron, here's your right aileron. I want you to keep that in mind for controllability. The elliptical wing is ideal for flights at slow speeds, and it provides a minimum drag for a given aspect ratio. It's harder to construct because of all this curvature and stuff. It's not like a rectangular wing. Some, rounding out has to be done on these wings and stuff like that. So it's harder to construct, and it has bad stall characteristics. Now, remember when I talked about ailerons being on the outside as far as control surfaces? This is how the stall patterns start to come in. When airflow separation comes, it starts at the back and it creeps forward. So the ailerons will be out here, and you have little or no controllability from those ailerons at this point. Whereas a rectangular wing, slower flying airplane, the ailerons are out here on the wingtip. So even as you start to progress into a stall, you still have some controllability of the aircraft when that happens. Here, bad stall characteristics. Look, it's just running all over the aileron. Same here, same here, same here. Alright. These are different planforms. They have different advantages and stuff like that. And you can freeze frame, and you can read about these on your own. And we talk about tapering. It provides a decrease in drag, increase in lift, which is most effective at high speeds. So you can see the tapers going on in the different slides. In swept-back wings, these are more or less found in like your jet aircraft, transport aircraft, and stuff like that. They're very efficient at high speeds, but at low speeds they kind of suck. But at low speeds, there's other little options that we're going to discuss later. But after we determine what our planform is going to be and everything, and we make the wing, then we mount it. Usually, it's attached to the fuselage with the wing cord. Back to our airfoil terminology, the cord separates the upper and the lower camber of the airfoil or wing. Alright, it's kind of pointed upward a little bit. And this point upward is called an angle of incidence. It's the angle between the longitudinal axis of the airplane, which is right here, nose to tail, and then they kind of angle it up a little bit. So the plane or the wing or airfoil already starts off with a little bit of an angle of attack. High lift devices. High lift devices are designed to increase the efficiency of an airfoil at low speeds. So this goes back to our swept-back aircraft. At higher speeds, very effective. Low speeds, they get really, really crappy. A wing flaps actually kind of delay the stall. Gives you a new angle of attack. Don't look at the dark lines, but this relative wind, just stay with this relative wind. And when the flaps were retracted, this was actually the chord line. But when we extend flaps, then we have a new chord line. And we actually delay the stall. We get more curvature in the wing, more Newton's third law of motion, action, bang, reaction, causing lift. But we get some drag too as well. But we get more curvature, more lift. So we have a couple things going on here. The most common high lift device is a trailing edge flap. And here we have a couple different types of flaps. Now when a flap is retracted, this is what it basically looks like. It's a basic airfoil section. When we extend the flaps, then we don't have the basic airfoil section anymore. We actually have something coming down and protruding. The first flap we're going to talk about is the plane flap. It's the simplest of the four types of flaps. It increases the camber or curvature. So we already had curvature, but now we got more curvature going on, and we increased the coefficient of lift for a given angle of attack, as we saw here. more camber, more curvature, new angle of attack. Alright. Increased coefficient of lift. Now we get a lot of drag, and it moves the center pressure, which we'll go into detail about, but its center pressure is where the lift is basically concentrated. The next flap is a split flap. It just kind of like hangs down, like it just kind of drops down like this. Doesn't slide back or anything like that. Alright. The flap is deflected from the lower surface, and airfoil produces a slightly greater increase in lift than the plain flap. More drag is created because, boom, there's nowhere for air to like escape. It's like, hey bro, it's like sticking your hand out a window of a moving car on the highway. A lot of drag goes on. But both of these, the plain and the split flap, produce high drag with little additional lift. I mean, they do something. So, I mean, don't look at it like, oh, a little. It does do something. It delays the stall, increases coefficient of lift. Now we have a split flap. Now, we're really increasing coefficient of lift more importantly than our plain or our split flap. And actually what's going on is we got higher energy air. We got the curvature going on, and this high energy air is like, boom, coming over here. So you got airflow coming over here, you have air flowing on the bottom of the airflow, and then becoming a part of this new airfoil. This is like a whole new airfoil. And here you can see this, you can see an opening, you can see the slot, you can actually see through it when they're extended. So higher energy air from the lower surface is ducted to the flap's upper surface here, and we get a lot of extra lift going on there. And then our last type we're going to talk about is the Fowler Flat. Alright. This flap not only changes the curve of the wing, or camber of the wing, it also increases the wing area as it slides backwards on tracks. The first portion, when you start extending these flaps, they really help. Increased lift, a lot of drag, but then you get to a point where when you're landing, you want a lot of drag going on. Alright, so here I just included a Fowler flap situation, and just watch the difference of how, see where the trailing edge is now, and then we extend flaps, man, and we get more surface area, whole lot more curvature. We'll go back to the retraction part, and we'll just do it again. We'll start a couple notches. And then another thing too I want you to pay attention to is we actually have leading edge flaps, alright, on that side, so you can actually see how, as the system slows down, slows us down. We got a lot of drag going on in this situation, but we have some leading edge flaps which actually come over the top of the wing and really get a lot of air circulation going on. But at this point we're landing, and we'd be deploying flap spoilers next at this point. Now back to drag. We talked about drag, 4 forces of flight: lift, weight, thrust, and drag. And we said drag was not by itself. Drag's not alone. In this sample, drag equals parasite drag and induced drag. So drag is the opposite of thrust. It opposes thrust, backward or retarding force, but there's two subcomponents: parasite and induced drag, and we're going to talk about them both. Parasite drag is caused by any surface which deflects or interferes with the smooth airflow around the airplane. The landing gear here, for instance, they're messing with the smooth airflow. Now, parasite drag is actually broken down into 3, so it even goes deeper. We have form drag, interference drag, and skin friction drag, and we're going to discuss those. Here's form drag, and this comes back to our first slide in this lesson that I showed you. Form drag results from a turbulent wake. Like sticking your hand out of the window, it causes a turbulent wake. When you're in that moving car, you stick your hand out, it's causing a turbulent wake, and you can feel it by your hands bouncing around violently. Say if you're on the highway, 65 miles an hour, on the passenger side, of course, not driving, you just stick your hand out the window, it causes a turbulent wake. And this kind of looks like what you do when you stick your hand out the window. A lot of disturbance going on. Alright, but we can see streamlining taking effect to where we got the flat surface, then we got the ball, still some distortion. We put a sphere with a fairing on it, and then we put it all in the housing, and we have very little air disturbance. So streamlining reduces form drag. The amount of drag is related to both size and shape of the structure which protrudes into the wing. Alright, so streamlining is how we get rid of form drag. Just having something out there causing, just being stuck out there causes form drag. Interference drag. It occurs when varied currents of air over an airplane meet and interact. Just having something out there in the air by itself may not be so bad, but when you actually connect two parts together, like the wings and the struts and the fairings and the landing gear struts and all that and everything, you may have one object there, but when you start connecting stuff, then just things joining together can produce turbulence of or drag of 50 to 200% greater than any parts. Excuse me. Tested separately. So interference drag is the mixing of air over structures such as wing, tail surfaces, brace, struts, and landing gear struts. Excuse me. Skin friction drag. Skin friction drag is caused by the roughness. Now, although the wing may look smooth, you can rub your hand over it and it looks smooth. When you put it under a microscope, you could see air molecules getting trapped in all kinds of eddies and stuff like that when we put this wing under the microscope. So that all is what parasite drag is comprised or composed of. Another thing we need to notice about parasite drag, and again, don't let these diagrams will fool you, or these tables fool you. It's not, anything to be scared of. All it's showing you is parasite drag is 0, and then our airplane in slow, and in high speed cruising. Alright. So as we increase airspeed, the parasite drag starts at nothing, it's slow, and it's low, and it actually increases with airspeed. So it's kind of like that ton of bricks on our tail going, no, hold up, wait for me. Like, you're a drag, parasite drag, because you're trying to slow us down all the time. Or not so much when we're slow, but when we speed up. You really get antsy and you really want to slow our plane down. Now, we talked about parasite drag as part of total drag. Now we need to talk about induced drag. Okay, like we said before, we have lower pressure at the top, higher pressure at the bottom of the wing. Now, as this plane flies through, the high pressure is on the bottom, the low pressure flows at the top. Now what happens is, as the air flows over the wing, this air meets, or these air molecules meet each other at another point, back here at the trailing edge. And what happens, this mixing of air causes something called a vortex. That's singular, a vortex. When you're talking about two or more vortex, we call them vortices. So vortex, vortices, plural. So this is a vortex. Now, what happens is the air molecules meet each other after being disturbed at the wingtips and at the trailing edge, and it feeds into this vortex. Alright, so that's how we get our wingtip vortices. Low pressure on the top, high pressure on the bottom, meeting each other at the wingtip and the trailing edge, and then it forms these little small hurricanes or disturbances in the air. Now, induced drag is just a byproduct of lift. Alright, and total drag is funny because it always has us. If we look at our chart here, total drag is here, airspeed is here. as our airspeed increases at low speeds, induced drag is high, right? And then as we get up, it goes to zero or it gets very low. And then, but another thing is when induced drag drops off, then form drag picks it up, right? So total drag is always going to be with us all the time. But it's important that we talked about the parasite drag, which is parasite drag, form drag, interference drag, skin friction drag. Induced drag is just the fact that we're creating lift. Air is flowing over the top and the bottom, low pressure air, higher pressure air, meeting each other at the trailing edge of the wing and the wingtips. So drag's always with us. It's like the Force on Star Wars. It's always with us. So one thing, those vortices that are created, they fall and sink behind the aircraft as the aircraft flies through. And we need to avoid wingtip vortices when we're flying behind larger aircraft. Finally, what I want to talk about is ground effect. Alright, now when we're up here flying high, we have our normal upwash, downwash going on. But when we get closer to the ground, we have reduced upwash, downwash effect. And the Earth is actually interfering with the airflow patterns about the airplane. Hence ground effect. Ground effect's messing with us. Now, what happens is when we get down, induced drag is actually it's diminished a lot. It's reduced a lot, I should say. So a couple things could happen. The airplane can be airborne before its recommended takeoff speed. You say, okay, we're supposed to rotate at, I don't know, let's just say for our purposes, you rotate at 70 knots. But you actually become airborne at 50, and you're like, wow. What you need to do is stay within one wingspan of the ground. So you're going to just fly over the runway. Then when you get your recommended takeoff speed, then you can pull your nose up and climb out. But when you're in the ground effect, when you take off, you'll become airborne before the recommended takeoff speed. Conversely, when you're landing, you'll feel like a cushion of air because you come down within one wingspan and, oh man, it feels like a cushion. If you add any excess power or you do any excessive flaring, i.e. pulling the nose up a little bit, the airplane will just hang. It doesn't want to land, doesn't want to land. And then you got to be careful because you should just go around at this point. But some people have just let the airplane settle to the ground and they try to stop on the remaining runway instead of going around and touching down like on the first third of the runway or whatever their target is, the numbers. So you want to be careful because the same lift is there. That's what you have to understand. When ground effect takes place and you're within one wingspan, you got that same lift, but you lost induced drag. Remember, in flight, we had our total drag. We had paraduced drag and induced drag. Then we get here, the induced drag comes out of the picture. And so we either float a lot when we're trying to land, or we become airborne before our recommended takeoff speed. Now, the worst thing you could do is try to keep climbing, because then what happens when you get outside of a wingspan height above the runway, then you're going to abruptly settle back down to the ground because the induced drag is going to be, hey, I'm back, buddy. And then you won't have the recommended speed, because airflow flowing over the wings is what causes lift, and you need it at a fast enough rate, i.e. indicated airspeed. So if your recommended airspeed is 70 knots, you don't want to climb out of the ground effect. But when you do your flight training, your instructor will cover all that stuff with you. But this is just to give you a little tidbit of what ground effect is. So that's basically it, my spiel. We talked about ground effect. We talked about parasite drag. We redefined drag. That was very, very important. I'll just flow back and we'll, just to recap. It's not a problem. Alright. Alright, so to recap. We talked about aerodynamics, the science that deals with the motion of air and the bodies acting on it. We talked about vectors. We talked about the four forces of flight. We talked about Sir Isaac Newton and what he contributed to aviation, and Daniel Bernoulli. Sir Isaac Newton gave us our 3 laws of motion. Daniel Bernoulli used the 3 laws, or Sir Isaac Newton's work, and he expanded and came up with his Bernoulli's principle in a book called Aerodynamic. In order to demonstrate what happens in Bernoulli's principle, we need a Venturi tube. And we talked about his principle as the velocity of an air increases and its internal pressure decreases. Newton's 3rd law of motion: for every action there's an equal opposite reaction, thus giving us lift. We defined airfoil terminology, or we gave you airfoil definitions. We defined airfoil terminology. We gave you the definitions: leading edge, trailing edge, upper camber, lower camber, chord, relative wind, angle of attack. We talked about air circulation and center of pressure, low pressure on the top, higher pressure on the bottom. We talked about coefficient of lift, how we hit what's called CL max, and then we actually lose lift if we keep increasing our angle of attack. So if you're not an F-15 or F-16, we won't be doing that with our airplanes, will we? No. We talked about stalls, airflow separation, aspect ratio, plan forms, angle of incidence, flap types. We did our little demonstration of what happens with our wing. We redefined drag, which is parasite and induced drag together. Parasite drag is formed by interference drag, form drag, and skin friction drag. And induced drag is produced by it's a byproduct of lift. And we looked at our chart here for total drag, and we could see that drag will always be with us, whether we're at low air speeds or high air speeds. Just think of this as a number line, right? At low air speeds, we got our induced drag is up. Our form drag is really, really low, right? But then as we increase our airspeed, the induced drag goes away, but the form drag says, okay, I'll hold your hand now, that you can fly faster. So total drag is always with us, constantly. There is a point where it's minimized in airspeed, but it's basically always going to be with us, and that was basically my point in the lecture. Then we talked about ground effect. Okay, ground effect occurs within one wingspan of the runway. Okay, and it's basically an interference of the earth with the airflow patterns about the airplane, and we could become airborne before recommended takeoff speed, or we could have a cushion because the induced drag has kind of gone away due to the disruption of airflow. So I didn't put my last slide in, but you can see it on the first slide. I'm Kieno Thomas. If you have any questions, comments, or concerns, you can email me at KIENOTHOMAS, KienoThomas@gmail.com. And in the subject box, please put aviation, so I know it's aviation related, as I do a lot of engineering work, mathematics, and things of that nature. I thank you for watching. Have a great day, and be safe.